Hello everyone, I am Amihay Elboher, an MSc student at Ben-Gurion University, presenting our work on Metareasoning for Interleaved planning and execution. This is joint work with Shahaf, Shperberg and Eyal Shimony from Ben-Gurion University and Willer Ramel from the University of New Hampshire. I would like to take this chance to thank them for all their help and guidance. We begin with some motivation. Numerous planning and search problems contain temporal constraints, such as actions that need to be done at specific times and deadlines. Since planning is a hard problem, assuming that it is done instantaneously is unrealistic, thus one must take into account the time spent deliberating. A planner aware of this is a situated temporal planner. In standard situated temporal planning, the plan must be complete before starting to act. The planner should prune potential plans where at the time planning is projected to end, the resulting plan is already expected to be tardy. For example, if your plan contains train travel, the planner must take into account that the train leaves at a specific time. Is unrealistic. Thus, one must take into account the time spent deliberating. A planner aware of this is a situated temporal planner. In standard situated temporal planning, the plan must be complete before starting to act. The planner should prune potential plans where at the time planning is projected to end, the resulting plan is already expected to be tardy. For example, if your plan contains train travel, the planner must take into account that the train leaves at a specific time. In standard situated temporal planning, we assume that planning terminates before execution begins. A deadline for execution of the complete plan is also common, as in the following scenario. In this scene from Die Hard, exactly 4 gallons of water need to be placed in a 5-gallon jug, using only additional 3-gallon jug and an unlimited source of water, before the bomb, set to 2 minutes from now, explodes. If the deadlines are very tight, as in this scenario, one just cannot spend too much time deliberating before beginning to act. It may be possible to gain additional time for deliberation by starting to act actions from a partially developed plan. However, starting to execute actions without having a complete plan is also hazardous, as actions may have to be undone or even have immediate disastrous consequences. Balancing this trade-off is the focus of this paper. This paper develops a disciplined meta-reasoning methodology for reasoning about the trade-offs between which potential plans to develop and when the gain from taking such potentially hazardous actions outweighs the risk therein. We aim to maximize the probability of a timely and successful execution. For example, in the jug filling scenario, it seems that starting to fill up the 5-gallon jug, even before being certain that this action is on the path to a solution, is a good choice. Note that in this work, we interleave planning and execution solely in order to find and execute plans before their deadlines, not to handle uncertainty or replanning. Let's move on to formalizing the problem. Considering the following example from the paper, where we have a flight we need to reach in 30 minutes. Our planner has already developed 2 candidate partial plans to get to the terminal, one using a train and the other using a taxi. Each partial plan has some initial actions, but the rest of the plans has not been fleshed out yet. Here is the search tree produced by the planner corresponding to the example. Note that our scheme is meant to represent search algorithms that work by adding actions starting at the initial state, as in the figure. A fringe node V thus represents a partial plan that begins with the actions on the edges leading to V. For example, fringe node B represents the partial plan take elevator, ride train, which we call the prefix of the partial plan represented by node B. Our meta-reasoning problem is to decide at each point in time which nodes to expand and which actions to start executing, if any. An action incompatible with node's prefix invalidates it. For example, we could consider executing the take elevator action and at the same time expand node B. Doing so allows us additional time to deliberate if there is a valid plan that begins with the take elevator action. But the call action is incompatible with take elevator. So this part of the search tree is invalidated and pruned, which makes the agent fail if the taxi plan is the only get to your flight on time. Note that although we assume a deterministic and fully observable environment, at this point in the search, we do not know how long the rest of each plan, shown as Ri in the figure, will take to execute. In order to be able to reason about risks and rewards, in addition to the prefix of each partial plan, we assume the availability of some estimates of the following quantities. 1, the overall deadline for this partial plan. 2, remaining planning time for this partial plan. 3, duration of the current unspecified rest of the plan. We assume that these are random variables quantifying this uncertain information. Additionally, during search for a plan, nodes are added and pruned dynamically. This makes this task of even defining the problem in a disciplined way very difficult. We thus resort to an abstraction similar to the AE2 model of Shperberg et al. 2019, which tackles a similar problem in standard situated temporal planning without interleaving. We abstract away from the search mechanism and just represent each fringe node by a separate process working on this node and possibly its descendants, without further considering the search tree as shown on the right. Each process is associated with its plan prefix hi, the initial actions to reach the node, as well as the following random variables: remaining execution time distribution, Ri, deadline distribution, xi, and time to complete the search under the node mi. In our example, we have a known common deadline for both partial plans, which is 30 minutes from now. The prefixes are indicated by H1 and H2 as shown here. In addition, suppose we have different possibilities for completing the partial plans as shown in red. For example, we still don't know the payment method after the taxi ride, and we have probabilities over these possibilities giving us the random variable R2. More in general, we formulate our interleaving planning and execution meta-reasoning problem, IPAE for short, as follows. We equate the search under each of n fringe nodes with a process that tries to find a solution to the problem. Thus, we assume n processes where given are: 1, each process I has already computed a possibly empty action prefix hi. 2, for each process, the following distributions are known: mi of t, the probability that process I will find a plan given runtime t or less; di of t, an induced deadline distribution, the time by which process I must find a plan, as well as finish executing all the actions in its hi. The random variable di equals xi minus ri, so we no longer need xi and ri. Meta actions that can be taken at each time unit are: ci, assign a processing time unit to process I; ai, optionally in parallel with deliberation, start executing the next base level action in sequence from hi. This option can only be invoked if hi is not yet been invalidated and no other base level action is executing. Note that there are constraints on when a base level action ai may be executed as stated in the slide. The actual values of the above random variables for process I become known upon termination of process I. Given all the above, the problem is to find a policy for allocating processing time and action execution so that the probability of executing a timely plan is maximized. Termination is timely if the rest of hi can still be fully executed until the true induced deadline of process I after the process terminates. Continuing our example, we have the induced deadlines as shown at the top. Now, suppose that the computation time distributions are as follows. Process 1 will always terminate in 7 minutes, and process 2 will terminate in 1 or 8 minutes with equal probability. Now we have a fully specified IPAE instance example, and here is the optimal meta-level policy. We start by allocating computation time to process 2. If we find solution by 1 minute, then we start executing the taxi plan. Otherwise, we start to execute the trained plan while continuing the search in order to elaborate it into a complete plan. Now that we have defined the formal problem, we turn to discussing complexity and algorithms for solving this problem. Our IPAE problem setting is just like the model of AE2 in prior work, extended to allow for executing actions before a complete plan is found. In fact, an IPAE problem instance where all the HI are empty is an instance of AE2, where one only has to allocate the computation actions. This allows for several observations and the roadmap for tackling the problem. First, since AE2 is NP-hard, obviously our problem is also NP-hard. Second, can we leverage off methods used to solve AE2 into schemes that solve our IPAE problem? More specifically, in AE2 with no deadlines, a dynamic programming scheme was shown to be able to find an optimal policy in pseudo-polynomial time. Can this be generalized to our present problem, IPAE? Also, greedy algorithms did well in AE2. Would that work for IPAE as well? Note that IPAE is a meta-reasoning problem, so policy-generating algorithms need to deliver meta-actions very quickly to really be of use inside the planner. As stated just now, the IPAE, one way to tackle IPAE is using AE2 algorithms. For the special case of non-induced deadlines, we can convert one instance of our IPAE problem into multiple AE2 instances, each of which we can solve efficiently. Suppose we knew when actions are to be executed in IPAE, then we can represent action execution by deadlines and convert the IPAE instance with this additional assumption into an AE2 instance. We do this by appropriately setting additional deadlines for each process, as shown by example in the following slide. This is an example of how to do this reduction for a specific action execution time configuration. Suppose we have a process P with the deadline distribution shown in this slide. Incorporating the above configuration of executing AY and N2 and A2 result in the effective deadline distribution at the bottom of the slide. This is done by moving the tail of the probability mass to the time when the process becomes invalid given the action execution time configuration. Can we use dynamic programming for AE2 in order to solve in IPAE? Since we don't know when actions are to be executed, we need to consider all possible start times, exponential in the number of actions. In practice, we can try several configurations. Each results in an AE2 problem instance, and take the best among them as an approximation. In some spatial cases, we have exact solutions in pseudo-polynomial time. Spatial case 1, bounded length prefixes. Spatial case 2, equal slack. For more details, refer to the paper. For the general case of unknown deadlines, we have two classes of IPAE algorithms. One, reduction-based as described above. Two, demand execution-based. In the latter, run an AE2 algorithm, but whenever computation time is about to be allocated to process P, check whether it requires execution of some action A now and execute it. We have begun an initial empirical evaluation, still very preliminary, and we are working on extending it to actual planning domains. In addition, the algorithm quality results are somewhat unstable and require further examination. two specific algorithms seem promising. The reduction-based max-let algorithm is based using a basic greedy scheme, BGS, after fixing action execution times to the latest possible time. The demand execution basic greedy scheme algorithm uses demand execution on top of the basic greedy scheme. Both these adaptations seem to do better than the unadapted AE2 algorithms, dynamic programming, and basic greedy scheme. See the paper for the algorithm details. To conclude this talk, we state the contributions of this paper and some directions for future work. Thanks for the attention. Any questions, comments, and ideas are welcome.
Thank you, Amihay. Do you have any questions from the audience?
I see some hands.
I think they are clapping, not raising hand.
Okay. Oh, sorry. Yeah.
Okay. So I have one question. So in your work, you say that you don't know the exact deadlines, but you have some probability distribution about the duration and the deadlines. But in order to say to extend the work, like can you think of any ways in which you can handle uncertainty in the probability? Because for integrated dynamic events, even estimating these probabilities are not easy and they may be inaccurate.
That's correct. If I understand your action well, then note that we abstract away from the search mechanism. So I assume that I have the distribution. Since I have the distribution itself, I don't need to worry about whether the estimate of the time of the rest of the plan is accurate or not. But if you ask specifically how to make experiments, then the question how to get the distributions is I think that it's a bit more than what I tried to show in this paper. Mm-hmm. So maybe it would be better to take a look in the paper and see how we exactly did it.
Great.
Anyway, we did it by collecting information from prior data, which we succeeded to solve on other distances.
Okay.
Basically, this idea.
Okay. Yeah, that makes sense.
Thanks for the question.
So, Amihay, can I add to this answer? I'm also one of the co-authors. So we've actually integrated this scheme into the optic planner for the case of planning, finding a complete plan and then execute it. So for that case, we've actually generated distributions online using the planner by considering relaxed plan and taking one-step error from the search. So we already have a way to at least estimate the distributions, and so we can incorporate the meta-reasoning problem to the search using these distribution estimations we get from the plan.
Nice. Yeah, very sophisticated.
Oh, and it's going to be presented in ICAPS next week.
Okay.
Yeah. So let me add one last comment, unless Eyal wants to do it. If you have uncertainty about the distributions, you can just incorporate that into your distribution, right? That's basically Bayesian update. So you can ask the question of would higher uncertainty lead to different results than more accurate distributions or more focused distributions, which I don't know. Maybe Amihay can answer that. But in general, distributions capture all the information you need.
Yeah, thanks for the comment.
Yeah, of course, if the distribution is junk, then you get not such favorable results in the planner from our experience in the other paper.
Okay. So if we don't have any questions, any more questions, then we can move to the next talk. The next speaker is Yaniel. Are you here?
Hi, yes, I'm here.
Okay. So Yaniel will be talking about an integrated framework for remote planning.
Yeah, let me share my screen. Yeah, just let me know when you can see my presentation.
But now I see the whole PowerPoint. Can you do?
Okay, wonderful. Yeah, I'm just yeah. Is that
great?
Okay? Yeah. Wonderful. Okay. Yeah. So hello everybody. I'm Yaniel Carreno. I'm a PhD student at the Edinburgh Center for Robotics, and today I'm going to present our work in an integrated framework for remote planning. So robotic platforms provide the potential for safer operating solutions in remote and dangerous environments that would otherwise put human workers at risk. Basically, this work is really focusing on some of the problems that we have been facing as part of the Orca Hub project that is involving 5 universities here in the UK. And we were just really focusing on trying to look for the big issues when we are trying to integrate planning into robotics applications. Solutions in that kind of settings face 2 main problems from our point of view. So the first is the uncertainty associated with extreme environments that often limits the deployment of fully autonomous systems. When we are, for example, talking about offshore energy platforms, and definitely because that problem with the deployment of those kind of platforms is required to have human supervision in most of those applications. So the second one is obviously the remote settings necessitate a variety of different robots with different capabilities, and is necessary to implement many times complex missions that requires coordination and collaboration. Obviously that in terms of supporting long-term operations. And for that reason, the direct human intervention ended up being impractical. For that reason, the contributions of this paper is proposing a symbiotic framework between mission specifications, planning and monitoring, each aiding the others and leading to the more user-friendly approach for remote planning. We need to remember that many of the operators that are actually based and leading the control of these robots not necessarily have a lot of knowledge regarding the characteristics of the robots, or let's say the environment, or in some cases about the planning technology behind the strategy. So the system integrates the following features. So the first, a user interface to facilitate the development and monitoring of remote missions by human supervisors. And the second, robust AI planning solutions for heterogeneous multi-robot systems that implement intelligent behaviors and in dynamic environments. So we can divide, this is actually the general system. And we can actually divide the different parts in 3 main areas. So the first one is the development, and the development is related with all mission specifications, defining the goals and available resources that we can edit in the problem when we are defining basically the problem in order, and then we can generate a plan. And the parts involved on this are actually problem definition and high-level task planning. So the second part is the review. So there we talk about analyzing, evaluating the proposed plan, ensuring that it is safe for the user in order to implement it later. So it is, let's say, like when we have the operator, is more like it is completely happy with the kind of performance that the planner is providing in the solution that it is actually presented to the operators. And then the last part, and this part is related with the visual plan inspection. And finally, we have the supervision, which is actually related with the plan deviation analysis and the remote mission monitoring. And then there we are talking about plan execution, assessing the plan deviations and guarantee in order to make sure that we have observability in the mission. So what we are going to do now is basically to describe the different elements in this framework. So the first one, problem definition. So the problem definition, we say that we divide it in domain model and editor interface, and they are obviously really, they are complementing each other. So the domain model is, we can say that this part presents two parts. So the first one is the system predicates that are all those statements that we don't know, we don't need to change. Let's say, for example, the positions where points of interest that we have in the mission, where we need to explore a particular motor or we need to explore a particular valve in the environment. The second part are those predicates that are the user predicates that represent statements that the user may update for specific reasons and for specific missions. Let's say, for example, robot starting points, let's say. And yeah, this domain model we are actually using as a main language the planning domain definition language. And what we actually tries to map this information from the planning, from the domain and the problem in a JSON domain model in order to interact with the editor interface later. So the editor interface is a part that we have a paper published last year in the just regarding this part, which is an interface basically for the operators to update the characteristic of the problem, you know. So for example, there we can update, for instance, the positions of a robot at the energy level that the robot has at the beginning of the mission. Then we have we can put the information regarding the goals and parameters associated to them. And finally, because we are working with temporal planners and planners that support preferences, there you can see in your right-hand side some elements regarding preferences and information that is actually very useful in order to optimize the performance of the plan output. This is the problem definition. So basically, when we have the problem definition, importantly, and actually the domain, we are able to generate the plan. So the point is, like, because we are working with multiple robots and robots with different capabilities, so we are talking about heterogeneous robots. We ended up being in a situation where temporal planners are not optimizing the task allocation. So it's not optimal enough in terms of the final output that we are expecting from the plan solution. And we actually have a paper from last year in ICAPS as well, describing this kind of situations of how we optimize the performance. But in that case, we were talking about underwater robots. So basically the strategy, the task allocation strategy was just focusing on completely decouple actions in a plan. In this case, we introduce as well coordinated actions. And what we have is a multi-role goal allocator method. So the multi-role goal allocator method takes into account the vehicle ontology. When we talk, I'm talking there is regarding to the capabilities that the robot presents. Also the mission points of interest, goal ontology, like what are the kind of capabilities required to implement the goals, the goal redundancy in the sensory system. Let's say like we have a robot that may fail during the implementation. Then in this parameter, what we are thinking is what happens if we have the failure for this particular robot with this particular sensor. Do I have a second sensor that actually can support the implementation of this action, or is just like I need to definitely replan from that point on? So all this kind of information is all these kind of inputs are taken by the multi-role goal allocator method, and it generates the optimal allocation, which is actually introduced as a set of instance of the predicate robot can act into my PDDL problem. let's say it's important to say that actually multiple allocator method is a planner agnostic algorithm. So it's a good thing in terms of we can use it with any other planner that is actually able to, at this point at least, able to deal with PDDL. However, we can even change the output if we want to use a different language. So having the domain on the problem, as I said before, we are using temporal planners. We generate a plan solution where we have multiple robots with different capabilities, in this case, Huskies and UAVs. And there are some particular actions in the plan that actually are implemented by two robots. So they are coordinated actions. The other part basically at this point we have already the plan solution, right? The operator can get this output in order to evaluate and see in a friendly representation, let's say, what is the output from the plan. Basically, it is a good point to evaluate if they consider that this plan is safety enough for them. So when I'm talking about this element, is perhaps operators can see that there are two robots that at some particular time during the mission implementation, when you can see actually the schedule here, there are some particular actions that perhaps are forcing the robot to stay very close, and that not necessarily is a good thing from their perspective. So they may think, okay, perhaps I can add a different preference in my original problem to force my planner to provide a different plan solution that restrict in some way the behavior of my robot. So this kind of thing, this is part of the visual plan inspection, because we can use this interface in order to evaluate that solution. And based on that final solution, the operator, can decide, okay, probably the best option here is change some initial some particular elements in the initial state, and let's replan even before let's generate a new plan, because we are not replanning at this state yet. So that is the important things with the visual inspection. So let's assume that at this point we already have a plan that the operator is happy with. We ended up starting with execution and then with remote mission monitoring. So the remote mission monitoring for us is a framework called OrcaHub Simulator that unifies multiple autonomous systems, in this case, terrestrial and aerial vehicles. It's a ROS-enabled offshore energy structure composed of 4 towers. And the simulator provides a semantic description of the offshore energy structure, including semantic roadmap and autonomous point-to-point navigation and collision-free planning. And finally, so the system allows the robot to perform aerial inspection, monitor towers, check sensor states, turn valves, and record data. So this is very helpful, and I think we presented the initial system last year in the system demonstrations in ICAPS. However, it was not at the point that we are right now, because it has all the elements that I was describing. I will continue describing in the presentation. So having this basically our system, in terms of the remote mission monitoring, what we have is the platform that we were talking about here, where actually present the offline plan generation and then the execution. And we divided the architecture in 3 main parts. So the first is the planning framework, where we have all the information regarding the domain, and then we use a temporal planner, in this case Optic, to generate a plan. And then the second part is the plan execution framework. And finally, we have the plan deviation analyzer. So first 2 elements in our framework are basically our framework in general for plan execution is an extension for ROS plan. In this case, is on plan deviation analyzer and the multi-role goal allocator. And focusing on the plan deviation analyzer, what we have is like, I probably would like to show you some other, on the video here. Apologize because it's a long one. So basically you can see the different robots. Husky 1 is here, we have Husky 2 here, and then we have one of the drones in this position. There are some particular points where we are actually seeing the Husky scaling up to a different level. I have to say that this part is quite challenging. Sometimes it's quite hard, and it is required to replan from that positions. But in the reality, we are trying to be quite clear about what are the drawbacks of having this kind of implementations in real environments. In terms of a plan deviation analysis considers 2 different cases. So the first one is the case where failures are associated with implementation of the action that we have in the plan. Let's say that we are navigating from point A to point B. And then for some reason, the planner is not able, the executor is not able to complete the action in the expected time. So this is the case, for instance, that we have we have that roadmap between point to point, and perhaps for some reason there is an obstacle that is obstructing the navigation. So in that cases, what our PDA is doing is actually taking the sensor output in order to see and identify what is a kind of problem associated with the implementation of this particular action. And to do that, what we were creating is just adding a set of different problems associated with the environment that we are working, and creating a library to see what are to get information from the sensory system in cases where replanning is required, do some evaluation about the reasons for the replanning, and update the information considering current state. The second case is when we have a performance detection component. So this is the case that is more, we think about this one when we are implementing solutions in real robots. So this is the case that, for instance, we are moving from point A to point B, but we realize that at the speed that the robot is doing, for some reason, the robot is not able to reach the next point in the expected time. What can happen in that kind of situations where we are working with ROS plan in the original setting is like we can end up having situations where the planner, the system requires replanning. So what we do here is just like try to get some kind of predictions about how long does it take to reach the new position, and how much time do I have right now in order to reach that position. If that is not matching at any point, what the system is trying to do is advising the system to increase the speed of the robot, for instance, in order to move to the next position. And this is the case that we are reflecting in the second part. Finally, I just want to point out that in our system, we do performance evaluation, taking information from the framework to evaluate make span, planning times, offline, and obviously when we need to do replanning. All this information is in some way stored in order that the operator can get information that can be useful in coming in different scenarios, considering the characteristics of the robot. And basically, those are very useful. For example, if we are later using for probabilistic planning and we need to get some kind of information that is actually generating a better and more approximated model of the real environment. So thank you very much for your time. I'm more than happy to take any of your questions.
Thank you, Yaniel, for your talk. Do we have any questions from the audience? I see that Eric has unmuted himself. Do you want to speak?
No, just
okay.
more
Okay. Okay. So I have a question. So one of the challenges of remote planning is like, how do you, especially in integrated execution, how do you communicate the plan? And are there any, do you see any potential in which, in your domain in which the plan is not communicated perfectly? And how do you adapt to that?
Yeah, so this is a good question, and it was something that we were discussing initially when we were implementing the solutions for this. In this case, particularly, we are using a centralized plan. Okay. And one of the reasons is obviously, well, first, because we want to implement coordinated actions, right? So we know that when we have a centralized planner, we are in more control of the system, and because we don't have any problem about communication. So previous work that we actually presented last year, it was more about decentralized strategy for cases where, for instance, there are problems with communication. This is the case, for example, in that work, what we did was a domain based on underwater robots. Mm-hmm. So in these cases, it's quite difficult to end up dealing with the communication. So in that case, what we have is just like a decentralized strategy. Every robot is performing their particular tasks, the particular plan. So they are implementing the plan and generating. However, in cases where we need to still keep coordinated actions happening, what we do in that case is introduce at the initial state, in the same way that we were using with this strategy, the multi-role goal allocator, we are introducing a set of constraints regarding of the time that the robot needs to be at particular points. And let's say that we have a UV1 and a UV2, and they both needs to be at particular point to implement a particular action. So that coordinated actions, that was the solution that we found for this one. Mm-hmm. And at the same time, in these particular cases, what we have is at different time slot during the mission, the robot needs to go to the surface and try to get communication. Because this is the case that, for instance, different robots can share information regarding, for instance, the mapping of the parts of the environment that they were making on the water. So it's like a kind of shared autonomy, and this is in the way that we deal with it.
Mm-hmm. Yeah, makes sense. I have another question. So in your GUI, you have like several nice plots and which are like showing the plans and how things are proceeding. So is there any way in which the user can give feedback or interact with the plots, or say that, okay, I see that, okay, this is not going to work, and you should handle. Yeah. Okay. So
yeah, so exactly. Okay. If you've seen, in the plan visualization, basically API, what we have is we have this original plan, right? But we have a plan that is being generated for a particular initial conditions, right? But in that visual representation, we are able to change some particular conditions. So that's important, because then we can see what happened if we change preferences, or mm-hmm. what happened if we, so basically that is the possibility that we are giving the operator, because then the operator can ended up having like 3 or 4 different plans for 3 or 4 different sets of initial conditions, preferences, metrics to evaluate the performance. And that is why, in some way, why we use temporal planners, and mm-hmm. particularly because we have the way to put preferences on our system, in order to give more protagonism as we can to the planner.
Okay, yeah, nice. Okay, thank you for your talk.
Thank you.
The next speaker is Michael, and he will be presenting his work on Lila, which is about optimal dispatching in probabilistic temporal networks using Monte Carlo tree search.
All right, thanks. So hello everybody. Do you see me, right?
Yeah.
How much time do I half?
You have 15 minutes for the presentation, and then we have 5 minutes for question and answer.
Okay. So we share my screen. Hopefully. Okay. All right, so you should be seeing the slide right now.
Yeah, it's I'm seeing what I'm supposed to see. You can start.
Okay. So this is a joint work with the JPL, and it's almost also worth to say it's a work in progress. Right. So I will probably not be speaking for 15 minutes anyway. But yeah, I hope that we will spend that remaining time with interesting questions. So it's about indeed PSTNs, which are probabilistic simple temporal networks, and also about Monte Carlo research. So first, for the context, what's the problem? What is a probabilistic simple temporal network? So here, for instance, you will have a PSTN that represents the activities of 2 planetary rovers, let's say on Mars, for instance, and the objective. So you have the activities, you have time points here, and you have constraints, like time constraints between the time points. And the activities is to plan, the objective is to plan the activities such that you respect all the temporal constraints. That is, you achieve controllability. And what I mean by plan the activities, it simply means that you must choose the right time for each time point. And here, the time points that you can set by yourself are those ones which represent actually the starting time of the activities. So for instance, one of the decisions of the problem would be to decide whether or not I start driving my rover 1 at time 0, or do I delay the starting time T1. And whenever I finish the driving activity, do I start the experiment straight ahead just after driving, or do I wait a little bit, and so on? Because of course, I guess you got it, but there is uncertainty, especially here in some of the durations, right? So indeed, some of the activities have uncertain durations, and the main challenge here is the time window here, where you see that the 2 rovers, they must relay information with the orbiter, and there is a strict time window to do so, between 15 and 20 here, for instance. But anyway, and given probabilities that, probability distributions that describe the uncertain durations, the interesting question is, given this PSTN, whatever decision you take, actually, even if you assume that you would take the best possible online decisions, what is your probability of succeeding, of meeting the communication time window here? So this probability is called the degree of dynamic controllability. So it is the probability of succeeding if you are smart enough to take the best online decisions. All right. So the DDC is quite an important measure, because it would say whether or not one PSTN is a good choice for scheduling the activities, or if you should go for another set of activities, and so on. Okay, so yes, state of the art on computing or approximating the DDC. So the fact is that computing the exact value, this exact probability, is strongly NP-hard. So it's really, really complicated. And up to now, there were the only method that exists for computing this DDC were approximations only, except one work we did a few months ago, which was still an approximation, but with the guarantee of being a lower bound on the DDC. That is, you have now the guarantee of never overestimating, because the other approach were approximation without guarantee. That is, if the method tells you the probability of success is of 90%, for instance, well, it could be overestimated, and maybe the true probability is of I don't know, 64%. So of course it's not the same deal. So here we proposed a method with a guarantee of being a lower bound, which is nice, but which comes with the limitation of being only able to deal with discrete probability distributions and durations. Everything must be discretized. But thanks to that, anyway, this method was also one of the first one, actually the first one, because the other one was from our work also, being able to deal with any possible probability distribution, whereas the other method, they usually assume normal distributions or uniform distributions. But here, now with Monte Carlo research and this new approach, what we propose is something that has that can deal with any possible probability distribution, that can deal with continuous probability distribution, continuous times as well, and which is an approximation, but an approximation which is proven to asymptotically converge to the exact value of the probability, which is a very strong guarantee compared to whatever existed before, because here we converge to something that is a lower bound, but you have no guarantee on the quality of the lower bound. But here it converges to the exact true value of the DDC. So the DDC, just recall that it's the probability of succeeding your operations if you're smart enough to take the best possible decisions online. And well, playing with Monte Carlo research has other nice properties. Actually, it becomes quite easy to deal with weird probabilities, like exotic probabilities, like, for instance, endogenous uncertainty. I'm not even sure how to pronounce it, but it's endogenous uncertainty. It means that your probability distributions are not fixed, but the decision you would take at some point of the process will modify the probability distribution of future events. So there are links between the random variables, and it's a stronger link than just dependency, actually, because you can also deal with dependency, but here it's not only the outcome that influence other outcomes, but also the decision you take. All right. So that's something really tricky mathematically, of course, to deal. But here with MCTS, it's really easy. You can deal with any possible dispatching protocol if you're not interested in the DDC specifically. Dispatching protocol, it is just well, you can call a dispatching protocol an algorithm that tells you how you take your online decision in a more simple way than just saying, okay, I will take the best possible decision, which is usually unrealistic. So for instance, a dispatching protocol could be, I will start everything as soon as possible. All right. So indeed, you can configure our algorithm and CTS to compute the exact probability of succeeding under the assumption that you would start everything as soon as possible, which is not as clever as the DDC, but in fact it is maybe more realistic, because most of the time you would not have enough computational power online on the moment in order to take the best possible decision, right? And also the CTS approach is also really trivial to extend if you want to consider extensions of PSTNs, like PSTN with sources, with utility, with cutoffs, preconditions, and so on. All right, so so just an overview, right? I will be really quick, no mathematics, nothing, just an overview, but there is a lot of details in the paper, all right? That's the reason why I wrote the paper is not, it's just because I don't want to explain everything during the presentation, of course. So the main idea, of course, and I think you got it, is to use Monte Carlo research because, well, Monte Carlo research is quite a famous framework and I mean, famous paradigms, and it has shown to be really, really good at playing games. So here, the idea was to model, to formulate our PSTN as a game, actually a single player game against nature. And well, usually in classical MCTS, you don't have uncertainty, but there exists extensions that deal with uncertainty, like rolling a dice or something, and it implies what they call chance nodes, whereas your decisions are decision nodes. So, for instance, here, so for instance, T1 is a decision node, right? You will take the decision of starting the activity drive at whatever time you want. So the decision node here, so root is a decision node. I should have put it as a circle actually. And possible decisions are 0, so start T1 directly at the beginning of the operation. Another decision would be delay until 4.2 time unit, or delay a bit less until 1.8, and so on. So whatever decision you make, so let's say you decide to start directly at 0 here, then you take the decision for T2 and so on. I think maybe I messed up a little bit with the numbers here. Anyway, I think you got the idea. And here you see the 4 famous steps of Monte Carlo research. So you identify one node, which is alone, and you here, and you decide to expand it. Okay, so you generate children, and then you simulate the execution until the end of the operations. And finally, at the end of the operation, you backpropagate the result you obtained. And usually the result here is whether you succeed the operations or not. So did I successfully meet the communication window, for instance? But you can put other things in it. You can assess if you want to consider utility, for instance, like how many operations you achieve to complete successfully, what is the total utility of the mission at the end of the game, then you can just propagate this information. So you can extend to various, you can deal with various extensions of MCTS right here. And also maybe the most important function in MCTS is the expand function. That's actually there in the expand function that you describe, you encode the rules of the game. So we know the classical rules of PSTN, but you can encode other rules, like what about taking resources into account? So if I choose to delay a little bit some activity, maybe it will consume a resource, or if an activity takes 2 hours instead of 1, then I will consume more energy, and then you just update the variables according to the rules you encoded and so on. But what I want to say is that any extension you want to put in your PSTN, you just have to modify the expand function. So it's really easy to extend thanks to the MCTS framework, because the other steps just remain the same. So finally, the main challenge were, and some are still, So how to model it as a single player game, so that we did. Also, there is a fact that classical MCTS usually is made for discrete games, right? But here we have a continuous action space and a continuous outcome space. But fortunately, there has been some literature about some idea proposed about continuous spaces in CTS. So we used their result and their proposition here. Also, how to simulate the execution. We used what we call next first. So it's the protocol that I told you about, which simply aim at starting everything as soon as possible, because well, we observed that in practice it has quite good average success rate. So it was quite a nice nice choice for simulating instead of just simulating randomly. And an open question is how to reuse subtrees in in a dynamic fashion, because when you start the operation, you can still use Monte Carlo tree search to decide online the decision based on what happened. But in MCTS, what's nice usually when the tree is discrete, the game is discrete, is that one decision or one outcome would not vanish the entire tree. You could still keep the current subtree. But when it's continuous, the probability of having an outcome that matches with one of the nodes, existing node of the tree, is quite like 0. Anyway, so I'm done, and 16 minutes. So actually I was lying. So currently it's a proof of concept only, right? It's a work in progress. So definitely the experimental results are quite poor. Only proof of concept that shows that actually the algorithm behaves as expected, and it converges to values that we expect at the beginning. So it seems to work fine. But we should do, of course, a comprehensive experimental plan, which involves, of course, the offline problem of computing this degree of dynamic controllability. So beforehand, computing the probability of success. But most interesting is the performance of using MCTS in an online fashion, dynamically. And also, of course, compare with the state-of-the-art dynamic algorithm for activity dispatching, temporal dispatching in PSTNs. Okay, I'm done. Thanks.
Thank you, Michael, for the talk. We are running a bit late. So does anyone have any questions? We have time for one question. Okay, so I have one more of a comment than a question. Like you say that you model the MCTS as like a game against nature. However, I feel that like nature is not really working against us, right? It's like nature is on their own, and like we do our best to survive. So
yeah, it's more like playing against someone that doesn't want to play. So it just basically plays randomly. I don't know if it already happened to you. So nature plays, but randomly, without the willing of winning or defeating you.
Yeah, so that's why like we may need to adapt the MCTS in a different way than like assuming that nature is taking like the worst possible stand against us.
Yes, indeed. So in fact, the extension of, for instance, you would have minimax in a deterministic fashion, but with uncertainty, when some of the actions are just random, then you have what they call expectimax. And in fact, at some layer, you would take the maximum, and at the other layer, when you have a random action, then you don't take the minimum or the maximum. Like in minimax, you just take the expectation, or actually the average of the observations. And at one stage, you would take the maximum of the expectations at the further stage, which is expectations about the maximums at the stage below, and so on.
Mm-hmm. Yeah.
Yep.
Anyway, we are running a bit late, so let's move on to the debate. And Victor and Mac will be moderating the debate. So I transfer it to them now.